Alright, another question that might be a little difficult is question 10. It's the one using the Rydberg equation. It gives you a wavelength of 434 nanometers. And tells you that all Balmer series are going to end in n equals 2. So that means my final transition state is going to be n equals 2. Okay? Now remember the Rydberg equation, the one that they give you is delta E. So that's your change in energy is going to equal negative 2.178 times 10 to the negative 18 joules. That's your energy of your electron times 1 over nf squared minus 1 over your initial squared. Now what we're trying to find is what is the initial transition state? What excited state are we coming down from? So what we got to do first is we need to figure out what my energy is. Remember, energy is equal to Planck's constant times speed of light divided by wavelength. So we're just going to go ahead and plug that right in. 6.626 times 10 to the negative 34 joules seconds. If you guys don't have that memorized by the end of the year, then we're not using it enough. Times speed of light, so 2.998 times 10 to the 8th meters per second. We can go ahead and divide that by 4.34 times 10 to the negative 7 meters. Remember, nanometers is 10 to the negative 9. I have 434 of them, so it's just going to move it over 10 spots, or to 10 spots. So put that in your calculator. You got 6.626 EE34 negative times the speed of light, 2.998 EE8, divided by my wavelength, which is 4.34 EE7, make that negative. So my light is coming in, my energy that is being emitted at, it's going to be 4.58-ish times 10 to the negative 19 joules. And this is going to be the number that we're going to plug back into the Rydberg equation. So that's going to be our delta E. And because it's being emitted, it's going to be a negative number. So delta E is going to be negative this. So we're going to go ahead and plug that in. So I got negative 4.58 times 10 to the negative 19 joules equals negative 2.178 times 10 to the negative 18 joules. And then my NF was 2, so we're going to have 1 over 2 squared, which is 4, minus 1 over my initial state, which is also squared. Okay? Hopefully you're following up to this point. Once we get to this point, this is just an algebra problem. So we're going to divide both sides by negative 2.178 times 10 to the negative 18 joules. So let's go ahead and do that. I haven't rounded yet, so that's okay. I'm going to divide that by 2.178 EE18 negative. So I get some really small number. That's not looking right. So I got 4.58 EE negative 19. Divide that by 2.178 EE got 18 negative. There we go. That looks better. So 0.21 and 0.21. And that is equal to 1/4 minus. I'm just gonna put an X because it's algebra, but that's my initial state. All right. Now we can go ahead and algebra this. So we're gonna have 1 over 4 minus 1/4. So 0.21 minus 1/4. So we're just gonna do minus 0.25. Oops. Minus 0.25. About 0.04. Don't round it like this. Do it the right way, but I'm honestly super exhausted. But this is still going to work out. So we got 0.04 equals 1 over x squared. It should be negative still. So go ahead and just, this is also negative. Go ahead and just take the negative away. So divide both sides by -1. There you go. And we're going to go ahead 1 over x squared. So x squared. So you got x squared times 0.04 equals 1. both sides by 0.04. So your x squared is equal to, if you want to do the math, you can. But all you can do, there's a cool little button on your calculator if you didn't know, it's just 1 over x. So it's going to be 25. So x squared equals 25, square root both sides. And hopefully you know the square root of 25, so x equals 5. So that is your transition state right there. Alright, so you're coming down from n equals 5 to n equals 2. Now something I forgot to mention up at the top is that this change in energy, that is your joules per photon. Now the second part of this question asks you what is the energy per mole. So what we're going to do is we're just going to set it up over here. We're just going to take this number, so you got 4.58 times 10 to the negative 19 joules per photon. Hopefully you can still kind of see that. And then we just got to do some dimensional analysis. So for 1 mole of photons, you have 6.02 times 10 to the 23rd photons. That's just Avogadro's number. Remember, that's how many things are in a mole. So your photons are going to cancel. And then we want kilojoules. So for every 1,000 joules, you get 1 kilojoule. So we're ending up in kilojoules per mole of photons. So that's going to be the numbers that you want. Let's go ahead and let's see what we get. So we got 4. Oopsies. Alright, so you got 4.58 times 10 to the negative 19. Just multiply that by Avogadro's number, 6.02 E23. Divide that by 1,000. So you should get 2.83 times 10 to the 2. And I'm going to make sure that this is actually right. Alright, so whenever you did the math, you got 4.58 EE negative 19. I'm going to go ahead and multiply it by Avogadro's number, 6.02 EE23, and then we're going to divide that by 1,000. So it's 275, not 283. So we can go ahead and change that. 2.75 times 10 to the 2 kilojoules per mole. That'll be your answer. So there you go.